Okay, we're going to discuss E1, which is elimination unimolecular of an alcohol, and we're going to do acid catalyzed elimination. So let's discuss a couple of properties about elimination. First of all, we know that elimination gives us alkenes if you have an alkyl halide or alcohol. So we're dealing with alcohols right now. So we know that E1 is going to proceed by way of a carbocation intermediate. That's kind of how we define unimolecular. It means that there's one molecule involved, and if there's one molecule involved in the rate determining step, we're going to form a carbocation. We can see that in the mechanism. We'll get there in a minute. But if that's true, if we're going to form a carbocation, then we know also that tertiary and secondary alcohols are going to be the most reactive alcohols toward E1. Once again, carbocation intermediates will be formed. Typically, we use large good acids, fairly strong. They don't have to be super strong, they don't have to be sulfuric acid. It could be phosphoric acid, for example, but it's still large and it's still a fairly good acid. Those types of acids will favor E1, and also alkenes, as we've already mentioned, are something that we're going to need to make over and over and over again. And so a lot of times, if you just have a straight up alkane, you'll first need to make an alcohol out of it, possibly, or alkyl halide, and then eliminate to form the alkene. So a lot of times when you do synthesis, you'll need to make the alcohol first from an alkane, and then we can make the alkene. So that's just a good thing to keep in mind when you're doing synthesis is, what can make what from what. And that's basically what a synthesis reaction is. So there's this thing called Zaxis Rule. And Zaxis Rule is basically an application of this thing called Regioselectivity. And regioselectivity means that the functional group prefers a specific part of the molecule. With alkenes, we prefer the more substituted alkene. And as we've discussed previously, we know that more substituted alkenes are more stable. And that's our reasoning for saying that. E1 also favors the more stable stereoisomer, as we've discussed. So when we have a mechanism favor stereoisomer, we refer to that as stereoselective. And so these are two important things to understand and to be able to differentiate them apart. We need to understand what stereoselectivity is, what regioselectivity is, and how they're different. And that will help clear up some confusion. And once again, we know that stereoselectivity is the reduction. The less the steric hindrance in the molecule, the more stable it is, or the less reactive it is. And so those are pretty much the properties and things to think about and look at when you're doing elimination. We have the mechanism here for E1, and once again, we're going to show the carbocation formation here, which is why we call it E1. So to start out, we have the alcohol become protonated by the acid, sulfuric acid. When we do that, we form a leaving group of water. It falls off. When it falls off, we have a carbocation. And the same molecule that protonated it is now going to be our base. And that's why we call it acid catalyzed elimination, because the elimination mechanism allows us to reform the acid with never actually using it up. And then we see that it gets regenerated in this step right here. And the electrons on the oxygen that we formed earlier are going to remove one of the hydrogens here, and the electrons in the hydrogen-carbon bond are going to fall down and give us a double bond there. And so you can ask yourself right now, did we utilize a stereoselective process here or a regioselective process here when we put the double bond there? So just to give you something else to think about, what if we had pulled off this hydrogen? What molecule would we get? And if we pulled this hydrogen off and we got this molecule, well, actually no, we wouldn't pull that one off. We would pull one of these off, right? Because the carbon's right there. Which brings me to a good point. Another thing that we can refer to elimination as is beta elimination. If this carbocation is the alpha carbon, then beta carbons are adjacent carbons, and the hydrogens bound to them are called beta hydrogens, and you can only remove hydrogens that are beta. So we couldn't remove this hydrogen here and get some alkene product because the carbocation is all the way over here. I hope that makes sense. But we can see that if we were to move that hydrogen, then the alkene that we get would be that. So you can ask yourself, which of these two products is more stable? Which one has more substitution? And so we would say that this one is more stable based on Zaxis Rule. The more substituted the alkene, the more stable. And so we used a regioselective process to make that molecule. And this product would be the minor product if we were to go through and form it. So just going to erase it just to be clear. That's the major product. And that's using Zaxis Rule that we would expect that one.